Thank you, Ted, Becca. And thank you, ladies and gentlemen, for being here. My name is Jeff Humpherys. I'm a professor in the math department, and I'm really excited to have this opportunity to share with you some of the things we're doing in the math department. We have a little background. There's a national shortage of STEM graduates in this country. And this is an area of significant concern. You see all these policy papers on the side there with Bill Gates testifying before Congress saying he can't find enough Americans to fill his positions at Microsoft. What is STEM? STEM stands for science, technology, engineering, and mathematics. And these four areas combine to give us the means by which we innovate and our way in which our economy will grow. Well, last year in February, the White House issued a report based on policy and economic analysts, the national academies, and the Defense Department, calling for a 34% increase in the next decade of STEM majors. This is very important for our entire economy, but some people might say, well, you can import or you can outsource the STEM expertise that you need. Well, one area where you really can't is in the Defense Department. We can't outsource fighter jet and missile design to other countries. We need that expertise here. We need to have the best and brightest in this country. And so we're very motivated by this concern. One of the biggest problems for why people do not go into STEM fields, based on the research, is what we call the math gap. We have not done a great job as a country in preparing our high school students to pursue careers in STEM fields. They look at all the math classes they're going to have to take when they get into college, and they major in something else. This is a major problem. And so we have to find ways of changing that. And so our goal at BYU, in the math department, is to attract and retain students in the mathematical sciences and STEM fields in general by empowering them with mathematics. One way we've done that is, for the last 6 years, we've been running what we call the IMPACT program. It stands for Interdisciplinary Mentoring Program in Analysis, Computation, and Theory. These are some different pictures of some of our groups over the last few years. This program is seeded by the National Science Foundation with a pretty sizable grant, and that got us started. Well, let me tell you a little bit about how this program works. So what we do is every year, every summer, we take 10 to 12 students who are just about finished their sophomore year, starting their junior year, and we put them through this very, very rigorous summer math boot camp. We call it boot camp for a reason. It takes about 70 to 80 hours a week of the students to work. So they're there at 8 in the morning, they've got classes, and then they've got assignments. They're often still on campus at 10 o'clock at night. This turns out to be a great thing. It really builds a work ethic amongst these students. And the focus of that content is mathematics, statistics, and computation. Then when they're done with the summer boot camp, we farm them out into different research groups across campus. These are some of them where we've sent a lot. We've got students economics and finance, engineering, computer science, and geoscience and chemistry. And then every week, the students come back together as the impact group, and they talk about their research projects with the other students in these other fields. And this brings some sort of cross-fertilization to what we're doing. The students see, oh, the thing that I learned in boot camp that I'm using in my research is also being used by this person over here in this completely different field. And we've abstracted away what it is that they're doing in the language of mathematics, and then it allows the students to be able to move fluidly across disciplines and to be able to see that they really are truly empowered by what they do and what they've learned. And as I mentioned before, this program was funded by the National Science Foundation. That grant has expired, but we've still been able to run this program on mentoring funds and corporate sponsorship, where companies have actually approached us to solve problems for them, and then those become the projects that some of the students work on. So today you'll get to hear from two students that have been in the IMPACT program. First is Matthew Webb. He's pictured here with his wife, Becky. Matt is a junior in mathematics, double major with music composition, as it turns out. Very talented guy. And he's been around from different places, but mostly claims Washington, D.C. and Brigham City as his home. Matthew.
Thanks, Jeff. As Dr. Humphrey said, I'm Matthew Webb, a junior in the math department. I'm very excited to be here with you today to talk a little bit about the research I've done. I was involved in the IMPACT program in the summer of 2011, and ever since then I've been involved with research in the math department. Now, one of the problems we've been looking at is disease progression, trying to predict early on when people might be likely to develop a disease. And I want to talk about a particular one today. Chronic kidney disease is a serious disease in the United States with a high prevalence. About 15% of people in this country have some form of the disease. As age increases, so does our risk. About 35% of people over the age of 60 have some form of the disease. As well, it's difficult to diagnose in the early stages. There are about 10 million Americans who have some form of the disease but don't know it. It hasn't been diagnosed yet. It can be very costly. $41 billion are spent every year on the Medicare population alone. And as well, it can be detrimental to families. Over 50,000 people die every year of this disease. So we wanted to create some methods that would help us using health insurance claims data to detect or predict the early incidence of the disease. Now I have a question for you. Have any of you ever talked to your phone before? When I say that, I don't mean talk to somebody else through your phone. I mean actually talk to your phone. It's pretty amazing that these little boxes we carry around can understand the words we say. There are sophisticated algorithms behind how that's done. When you first talk to the phone, it looks like a jumble of data. But what the algorithms can do is start to break apart and piece out the different syllables and the likely order of how things are placed, and can piece together the whole sentence that we said. So we said, why can't we do the same thing with health insurance claims data? And instead of predicting words, predict diseases. So we've abstracted away these algorithms to a different problem. And rather than looking at sound from a voice, we look at health insurance claims, and we try to predict and recognize the beginning of these different words, or in this case, diseases. So let me share with you some of the results we've had. This is what's called an ROC curve, and it quantifies how well we're predicting compared to random guessing. The green line represents random guessing, and the colored lines above are different models. But to better understand this, I want to choose a particular point, about right here, and see what does this mean for in practicality. So if we were looking at the Medicare population, where it's about 1/3 have some form of the disease, the results would give us something like this. We would classify people into two groups, those likely to have the disease and those unlikely to have the disease. And we can see we've identified a majority of those who are likely to have the disease. At this point, we can send letters or we can do further clinical testing to get them on the right track towards a healthier life. It's been a wonderful opportunity to work here at BYU. I'm surrounded by amazing, intelligent, and wonderful people, and it's been very uplifting and edifying to me. I'd like to thank everybody for the wonderful support for making this opportunity possible for me. Thank you.
Next up is Jeremy Bejarano. Jeremy is a senior double major in mathematics and economics, and he's going to talk about tax policy and using math modeling to come up with the best tax policy. Jeremy.
Okay, so like Jeff said, my name is Jeremy Bejarano. I'm a math and economics double major from Salt Lake City. And my research is focused on using supercomputers to solve mathematically complex models in economics, and in particular, in tax policy. So I put this picture up here just because, as Jeff might have mentioned earlier, because of the prevalence of tax policy in the media, it's easy to see the relevance of this kind of research. But I also put this up here because it illustrates one of the features of my research, my project. In macroeconomic research, the current trend is to build macroeconomics on micro-foundations. In macroeconomics, we make broad assumptions about certain interactions in the macroeconomy, whereas in microeconomics, we focus on the individual. So in current macroeconomic research, the goal is to try to take into account the fact that in the population, we have many different kinds of people with many different circumstances that would react differently to a particular tax policy. So as you can imagine, solving a model that takes into account many different types in the population would be very mathematically and computationally very difficult. So in my model, we take data that characterizes this population from the Consumer Expenditure Survey from the Bureau of Labor Statistics. We also take data on the distribution of income and wages. And this, coupled with theory from microeconomics, we can build predictions of how a particular individual would respond to any given tax policy. From this, from all these different individuals, we can sum those responses together and get an aggregate or national response. With these aggregate responses, we can perform analyses to determine what is the best or optimal tax policy. There's always a trade-off. One of the analyses that we can perform is, as you see here, each of these dots represents a particular tax schedule. Those red ones at the top are on the frontier. They're the most efficient. These are differentiated tax policies, or some are progressive tax policies. The yellow dots represent flat tax policies. As we would guess from theory, the flat tax policies are dominated by the red differentiated tax policies. But as you'll see here, it doesn't look like by much. So one of the questions we'd like to ask is, how does a flat tax compare to a differentiated tax policy? What sets this project apart from other similar projects is that this is one of the few projects in economics to make use of supercomputers. Our project uses the Mary Lou Compute Cluster at the BYU Fulton Supercomputing Lab. And this kind of research has gained a lot of attention. Last summer, I spent some time researching with a professor at the Hoover Institution at Stanford University, and last semester, I spent some time at the University of Chicago researching this problem. In December, the Department of Economics, in conjunction with this program that we're talking about here, put on a conference on computational methods in economics. Here in this picture on the left was Tom Sargent, who was the keynote speaker at the conference. He was last year's winner of the Nobel Prize in Economics. Here next to him is Professor Ken Judd and his wife, my advisor, and my wife and I. I just wanted to say I'm so grateful for this program that I've been able to be in. It's provided me with the opportunities that I needed to get into this kind of research and be able to perform it. I'm really grateful for BYU and for the opportunities that I have here. And I want to mention one thing at the conference. Professor Tom Sargent, in his closing remarks, said something, and this was very noteworthy. He said that he had never seen students prepared like these, and he had never seen a program like the program at BYU, this impact program. And he said he wished that every university could have that kind of program. Thanks.
Just a side note, Tom Sargent hired two of the students right away at the conference. It was to be his research assistants, and one of them he's made an offer to already for the coming fall to do their PhD with him, and then the other one will probably get an offer as well. So you've got to hear from a couple students that have been in the impact program. Let me have a minute just to tell you about what we've accomplished in the last 6 years and then where we plan on going with this program. So to date, in the last 6 years, we've mentored 63 undergraduate students, 19 of which have been from underrepresented groups, and all but 4 of which have gone on to some kind of graduate school, most of which have gone to top-tier programs. Yesterday, actually, Jeremy got accepted to the PhD program at the University of Chicago in economics with a very, very substantial funding package, and that is the sixth student in the impact program to get that offer from Chicago. So we've got a track record. Every year we've been able to do that, other schools as well have gotten into the habit of hiring 1 or 2 impact students each year that are also top-tier schools. So our graduate school and career placements have really been great. We've also produced several academic papers. We've got 20 so far, and several more are coming. The pipeline is pretty full. And we've actually got a patent pending as well on digital watermarking, where we developed a statistical method for embedding noise that you can't see into video that will allow us to detect who would have put it on the internet. And it will even survive changes in resolution or format. And so there's a technology there that we've developed, and we patented it through BYU's Technology Transfer Office. We've also experienced a significant increase in math majors, in part because of the impact program, 50% in the traditional sense, and if you account for double majors, which many of the impact students are, that's a 100% increase. We've also produced 2 marriages out of the impact program, and a baby. So I actually joked in my NSF report that this baby was supported in part by the National Science Foundation. Okay, so where are we taking this? We have a new degree program that we're putting together right now that will transform impact from this mentoring program, that this is extracurricular thing, requires a lot of funding, and it takes 10 to 12 students a year, to a degree program which will take 40 students a year. So we're ramping up on our scale. To do this, we've had to completely rewrite the undergraduate applied mathematics curriculum to make it so that we can bring all of these tools that they learned in impact into and produce a very modern curriculum. Tightly coordinated. The assignment that you do in one class, you're actually going to use what you did there in another class for a homework assignment later. So you're constantly re-seeing the things that you've learned. Next, it's going to be a lockstep approach. The students will come in as cohorts, kind of like an MBA program or an accounting program, where all 40 of them will come in and be in the same classes and move through the program together. We really like this. One of the benefits of the impact program has been that these students have very tight bonds. In addition to the 2 marriages, we've got some great friends and lifelong friends. And having this cohort approach in our program will mean that these students will network with each other for decades after they leave BYU. Every course in this new degree program has a computer lab tied to it, where the students will spend hours actually coding up and programming the algorithms that they've learned in their coursework, using huge data sets, and implementing high-performance computing technologies. Every one of them will use our supercomputing facility, for example. And these are undergrads. And we're also integrating research and mentoring into the curriculum so that the students, we don't have to compete with research and coursework and have conflicts, and students say, I've got a final, I can't do any research for the next week. Instead, we're going to have this program integrated so that they're doing research along the way, and it's part of the program. Finally, as has been a mainstay for the impact program, we're continually connecting this mathematics and statistics and computational approach with the other STEM fields so that the students will get to see the diversity of how their ideas can be employed. And the program starts in the fall. I'm actually on leave this year because I'm spending all of my time, most of it anyway, getting this program ready so that we can kick it off with a success. Along with the program, students will also choose an area of concentration. And we've already got 30 so far. And you can see, get a sense of how diverse the different areas are, that students of almost any interest in a STEM field will be able to come into this program and get tooled up with the mathematics, statistics, and computation necessary to really be great STEM problem solvers. And I just want to close my remarks with this quote by Richard Feynman. He's sort of a hero of mine, and he has this great quote about mathematics. He's a physicist, Nobel Prize-winning physicist. He said, "To those who do not know mathematics, it is difficult to get across a real feeling as to the beauty, the deepest beauty of nature. If you want to learn about nature, to appreciate nature, it's necessary to understand the language that she speaks in." So mathematics is the language of STEM. It's the means by which we analyze and abstract and communicate STEM fields, science in particular. And when I try to bring this back to the theme of the conference, firm and unchanging course, well, our courses are constantly changing. We're experimenting. We've just designed some new courses. And so it was a little ironic that was the theme given what we're doing. But then I realized, well, what isn't changing and what is firm is our commitment. And we've got to have this environment where we experiment and try new things and understand how science moves and be on the frontier. And so we've got to constantly adapt. But at the same time, we have a commitment to the students, and we have a commitment to this institution, and we have a commitment to the kingdom. Thank you.